In this video, I'm going to talk about how to use the Van 't Hoff equation to calculate the boiling point of water at a pressure that is not 1 atmosphere. So since we live in Lethbridge, we're going to use 90 kilopascals as our pressure because that's a fairly typical pressure for life in Lethbridge. And so if we look at what we're being asked here, we're being asked to calculate the boiling point of a liquid at a different from normal atmospheric pressure. Now, there's a lot of information in the question that isn't explicitly written in the question. The first thing to notice is that we are being asked about boiling point. So that means that we must be talking about the equilibrium for vaporization of water. So we must be talking about the reaction in which liquid water goes to water vapor. And we're being asked to calculate a temperature. We're talking about an equilibrium, and so that probably means that we would be making a comparison to another temperature. And so if we stop and ask ourselves about what temperatures do we know that relate to the evaporation of water, well, we know that the boiling point of water, the normal boiling point of water, is 100 degrees Celsius or 373.15 Kelvin. And so that is for pressure equal to 1 atmosphere or equal to 1.01325 bars. Okay, so we're getting somewhere. We've also been given the standard enthalpy change for this process. And so if we think about what our equation looks like, we have the natural logarithm of K2 over K1 is equal to delta H naught over R times 1 over T1 minus 1 over T2. We've now got information about our enthalpy. We've got information about one of our temperatures. We've got the ability to get to an equilibrium constant, I think, because remember that our equilibrium constant for this process is going to be equal to the activity of the products divided by the activity of the reactants. And so our reactant is pure water, so the activity of the pure water is going to be equal to 1. The activity of the water vapor is going to be equal to the pressure of the water vapor divided by 1 bar. So yes, we can definitely calculate the equilibrium constant that goes with that boiling point, the K2, because we have a number for the vapor pressure of H2O, and of course we have a number for the activity of water being 1. And so we can say, therefore, that K2 is going to be equal to 1.01325 bars over 1 bar. All that together is the activity of the water vapor divided by 1, which is the activity of the liquid water. So K2 is going to be equal to 1.01325. Okay, this is helping. What about K1? Well, K1, we want the water to be boiling with an atmospheric pressure of 90 kilopascals. 90 kilopascals is 0.90 bars. And so we should be able to calculate K1 as well, because that will be equal to the activity of the water vapor when the water is boiling and the atmospheric pressure is 90 kilopascals, which means the pressure of the water vapor is going to have to be 0.90 bars divided by 1 bar, and then that's divided by the activity of the liquid water. So we're dividing that by 1. So K1 is 0.90. And so we can fill that in up here. K1 is 0.90. So now we have information about K2 and K1 as well. And now the only thing that we don't have is T1, the temperature that goes with the vapor pressure of 90 kilopascals. And that's what we're solving for. So the most difficult part of this question is really decoding the information and organizing what you know. Once you organize what you know, yes, there's some algebra, and yes, there's potentially a log rule here or there, but you just practice and you get good at that. And frankly, you practice decoding the information as well. So now we can pick up all of this information and plug it into our equation on the next page. So we have the natural logarithm of K2 over K1 is equal to the standard enthalpy change for a reaction divided by the ideal gas constant is equal to 1 over T1 minus 1 over T2. We have established that the standard enthalpy change for this reaction is 40.66 kilojoules per mole. That was in the bottom of the previous slide, just data was given to us. We've established that T1 is what we're solving for. T2 is 373.15 Kelvin, the normal boiling point of water. The equilibrium constant for the unknown temperature, the equilibrium constant for the boiling of water at 90 kilopascals of atmospheric pressure was 0.90, and the equilibrium constant for the boiling of water at 1 atmosphere was 1.01325. So you have two choices depending on how comfortable you are rearranging variables, or if you'd prefer to put numbers in and simplify and then rearrange. It doesn't matter what you do. I'm going to start by rearranging my equation, remembering that we're trying to isolate for the 1 over T1. So the first thing I need to do is I need to multiply both sides by the ideal gas constant and divide both sides by the standard enthalpy change for the reaction. So that will get me R divided by standard enthalpy change times natural logarithm of K2 divided by K1 is equal to 1 over T1 minus 1 over T2. And then to isolate 1 over T1, I add 1 over T2 to both sides. So I'm going to get R over standard enthalpy change times natural logarithm of K2 over K1, all plus 1 over T2 is equal to 1 over T1. And if I wanted to isolate for T1, I would then take 1 and divide it by everything on the left-hand side of the equation, but that's too cluttered even for me. So I'm therefore instead going to start plugging in numbers at this point. And so I have 8.314462 joules per mole Kelvin divided by 40.66 kilojoules per mole. Remembering that I then need to convert my kilojoules into joules. And that makes everything except the Kelvin cancel out. Multiply that by the natural logarithm of 1.01325 divided by 0.90. And then add 1 over 373.15 Kelvin. This is going to get me 0.000024 inverse Kelvin plus 0.002679 inverse Kelvin. And when I add those up together, I get 0.002704 inverse Kelvin. And therefore, T1 is equal to 1 over 0.002704 inverse Kelvin, which is equal to 369.8 Kelvin, or 96.7 degrees Celsius. And so the boiling point of water in a typical Lethbridge day is not actually quite as high as 100 degrees Celsius. Because we are at reduced pressure, we don't have to get the vapor pressure quite up to the same heights as we would at sea level, and therefore we don't have to apply quite as much heat to evaporate quite as many molecules. This also means that when you boil your water, you're not actually heating your food to quite such a high temperature